Hello everybody! In this video, I'd like to talk to you about how the internet works. So, what is the internet? The internet is basically just a network of networks, and it's huge. There are so many interconnected computers along multiple different paths. The internet is designed to be redundant, so there are many ways to send an email from New York to London. There is a hierarchical way to structure the internet, so that you can go into smaller and smaller groups so that you can find each other. And along those links, all that's being sent is bytes. Everything is bytes. At a lower level, what is the internet made out of? Well, the points that are being connected are usually computers. They are servers, clients, phones, or things. We have the internet of things. So every endpoint that you're connecting to is some kind of computer. There are specialized computers known as routers that forward things called packets. Packets are fragments of messages, so it kind of just breaks everything up in a particular way, sends it to you, and then it gets put back together so that you can watch a video. The kinds of links that things are sent over include Wi-Fi and Ethernet and fiber. The internet can really just run over any sort of links. Common applications that you would use when on the internet would include, of course, web browsing. There's also email. There's the use of the cloud. So there's not just web browsing. There are these other things that are also being sent along the same network. So from your perspective, you are on your computer. You might type in a URL. And then your computer, which is the client, is going to ask another computer for some sort of information. So that's going to go to a server. The server might then have to go forward to some sequence of routers, which will go to another server, and then eventually that's all going to get sent back to you in a way that you can interpret the response so that a file actually loads on your browser and you can view a picture or a video or whatever it is you were looking for. So we access information using URLs, which stands for Uniform Resource Locator. The protocol for how that information gets sent is via something called HTTP. And let's think about a little bit what's actually being sent. Remember, everything is bytes, so even though you're typing in something like google.com, it gets converted into something computer readable, which are these IP addresses. I have here some examples of IPv4 addresses, which are these numbers between 0 and 255 separated by dots. And these numbers may not currently be correct because these do change over time. Each byte of the address is more specific, so it does set up this sort of hierarchy. You have what's called a DNS server, and it's got the root, and then that goes out to like the .com and .org and .edu DNS servers, and so on and so forth. The internet has this very particular structure, so if you're using an ISP, Internet Service Provider, and you're sending an email from New York, that's going to go to London pretty much immediately, but there's a lot of hops that it's taking along the way, and it doesn't necessarily take the same hops going forward as it would to come back. Between internet service providers, there's also something called peering. So even if your internet service provider is Google, it has some sorts of agreements with other ISPs like Verizon that it will use their routers or their hops to be able to send information. So the ISP has a structure which basically consists of a bunch of different routers. We also have the concept of hosting services. So you're on the browser, you send a request to the internet, and that might go through a hosting company. So you really just want the information from a particular company, company B, and you go to companyb.com, but they have data for you, and that data may not be hosted by company B itself. Most things are hosted through Amazon services, for example. So even if you think you're going to companyb.com, your requests are going to go through Amazon as well. That means that there are multiple parties that get involved in most web transactions. And that means multiple parties who know what is visiting, what visits are being made, who is visiting what pages, and who is receiving what content. Because of this interconnectedness, it's not really very easy to determine who exactly has the information for any given transaction. All right, so let's have this question of which is the browser and which is the server. They're really not different. It's just important what kind of software they run. So your laptop or your desktop is not going to tend to be as high-powered or specialized for returning requests at high velocities to millions of users as compared to a web server. But in the end, everything is just computers connected to one another. I'd also like to talk about the fact that we have a dumb network for the internet. The phone network originally, like with landlines, was built for dumb phones, and all of the intelligence is in the network for things like conference calls, call forwarding, and even voice menus. On the other flip side of that, for the internet routers are not very complicated computers. They're pretty dumb. Instead, all of the intelligence is at the end. Right? So even if it's going across all these hops, they're not really making computer decisions. It's just sending things forward. As a result, service providers are not necessarily the same thing as network providers, and it also means that service provision is decoupled from physical location. Your mail provider might be actually in another country. Okay, so we understand now that the internet consists of a bunch of different types of devices, which in the end are all computers, and they're connected through routers to send messages to one another. And the kinds of devices that you can have are laptops, desktops, phones, servers, and by phones I mean not just like smartphones, but also landlines. Now, I mentioned earlier that the internet sends things via packets, and those routers along the way are pretty low level. They're not really making decisions, but they are forwarding these packets, which are just fragments of messages. They are very, very fast. Each packet is going to be sent along a particular direction very quickly. We also have this concept of robustness. So if a router fails, packets can take a different path. And in this image here, I have a couple of different paths drawn out. The only thing that really matters is that the packet has a source and a destination so that you can have replies. Sending messages forward and having a message received back may not necessarily take the same path. Let's talk about IP addresses. When you go into your URL bar, you might type in something, www.dni.gov, and I mentioned before that gets translated into something called an IP address, which consists of these numbers. Let's talk a little bit more about what those numbers look like. They are 4 bytes long, so I have the number 23, and 23 is a number between 0 and 255, okay? So a byte is a number which in decimal is between 0 and 255. In other words, it takes 8 bits to represent. And then, of course, in this in the IP address, it's 1, 2, 3, 4 bytes of those. And it's a little bit more complicated than that because there are these content distribution networks, or CDNs, but let's not worry about that. IP addresses are what appear in packets, and then routers are going to talk to each other via routing protocols to learn where each of the next IP addresses are. The kind of IP addressing that I already told you about was what's called IPv4, with those numbers between 0 and 255 separated by periods. There's maybe like 4 billion of those, and we've run out. There's too many computers. We want to move to this new thing called IPv6, which is being deployed. It has many more addresses, although you can still use IPv4. It has 128 bits instead, and it is written as 8 2-byte hex values separated by colons. So here I have an example. So for a hex value, the numbers that you get are the digits 0 through 9 and then the letters A through F. And so you can see that there are 4 of them, and that in between them we have these colons, which is in contrast to the IPv4, which was just numbers, and I wrote those in decimal. So that's just how they're represented. Let's talk a little bit about port numbers. I said earlier that you could browse the internet, but you can also send mail, do other things. There are different protocols for talking over the internet, not just HTTP. If you are using mail, right, if you're sending email, you're actually using something called SMTP. All machines on the internet look alike. You can run a web server and a mail server on a single computer. So packets are not just going to contain an IP address, but they're also going to contain what's called a port number. So if you're actually trying to visit the web, you would use port 80. If you're visiting the encrypted web, you're going to use 443. Port 25 is the mail server. If you're SSHing to connect to a computer, you would use port 22. Think of an IP address like a street address, and then the port number is like the room number in the building. And actually, this is a nice little analogy. Think of room 25 as being the mailroom of a building, and room 80 is the library. And room 25 is the mailroom. Makes sense if it's the mail server. Let's wrap this up with talking a little bit about cloud computing. What is the cloud? Someone else's computer. It's a traditional way to represent a network, but cloud really refers to computing services that are provided via the internet by some sort of outside party. So in other words, the service is not provided on premises. You need an internet link to be able to access your files that you might be saving on the cloud. This link does provide an opportunity for interception, which could be legal, but doesn't have to be. So by definition, cloud services are provided by some sort of outside party. It is not the same as a company's own remote computing facility. An organization could have its own private cloud, but that's different from outsourcing it to a third-party company. The kinds of computing services that you might use are storage, computing applications, and virtual machines. And I think a lot of people are very familiar with using it for storage. Basically, there's disk location somewhere. It's easily shared, and it's often replicated for reliability. Somebody else is going to worry about that disk space, backup, security, whatever. And those things include Dropbox, Google Drive, and Amazon. You can also do computing on a remote computer. You rent computing cycles as you need them. You pay only for what you use. So if you have a sort of weak laptop and you need to do some high-powered computing, you can access things like Amazon EC2 or Microsoft Azure or Google Cloud to do computing for you. You can also run applications. So there's things like shared word processing. So Google's Gmail and Docs and Microsoft's Outlook and Office 365, it's like getting a contractor for a specific task. Google Docs is pretty interesting, actually. Someone using a web browser creates a document. It looks the same as if you had a Word document open and it was just local, right? Like more or less the buttons and the formatting is the same. Now, if you add someone to your Google Docs, if they have the proper authorization, then they can open up that document and view it and perhaps even edit it. Those changes show up in real time in everybody else's browser windows. So Google is not just doing things passively, it is noticing changes and sending them out immediately. Virtual machines, well, we have our own computers, like our normal desktops, which has an operating system and applications run on top of that. Virtual machines are a little bit fancier. but it's a single computer that pretends like it's multiple real computers. A different operating system can run on each one of these emulated computers, and each one is independent from the others. This means that many computers can consume the space and power requirements of a single computer, and it also means that you can have different operating systems available to you right away. So if you log into a virtual computing lab, then you can access different OSs. Like your computer might be Windows, but you can now access a Linux machine. How fast a cloud server is limited by how far away it is. It's the speed of light. There are, therefore, many cloud providers and server complexes in many places around the world. So where is this data stored? Email is usually stored on the server and on multiple devices. Users can't really tell what's on their device versus what is retrieved, and it differs from time to time. For security and privacy, Google applications do scan email and serve ads appropriately from that. Dropbox uses Amazon S3, but it does encrypt data so that Amazon can't read it, but Dropbox can. And those are the most popular ones. You might also be familiar with some of these other examples, but one thing I do want to point out is that email, almost no matter which one you use, they are going to check things, pictures for crimes, basically, and they are going to do spam filtering. Web pages are composed of many separate elements. Images are always loaded from a separate URL. There are things called frames, which are web pages that are embedded in other web pages from separate URLs. Many pages use JavaScript so that you can have responsive web pages, and web pages do web requests via HTTP, Hypertext Transfer Protocol, which contain the URL of the referring page. In other words, when you make a request, many websites are actually responding to you. You also have cookies. When you visit a site, you can have a cookie that is stored on disk, and when you return to the site, the browser sends back that cookie. This is very useful because HTTP doesn't remember anything about you. But if you want to keep your login or a shopping cart or site preferences like dark mode, you want to have cookies. They're also used to track people around the web. When you visit a page that includes other URLs, each site can set and receive cookies. There's a concept of first-party cookies, which are from the site that you are actually visiting, and third-party, which might be like ads being served up to you from another website. Most ads, in fact, are not served from the websites you visit. Sites deal with these things called ad brokers. And when you download a page, advertising image and frame requests point to these ad brokers. These third-party ad brokers get and set cookies, and they do redirect commands. You might block these with some sort of browser extension like uBlock, but this is a constant battle where sometimes you cannot receive a web page unless you are willing to view the ads. So in the end, you are being tracked around the web. If you click on a site and click on an ad for shoes.com, the cookie will be set by the ad network and says, this user is interested in shoes. You are going to end up seeing possibly more ads for shoes as a result. Now, since many web pages are involved, websites are involved, their log files are probably available as business records. Cookies are only accessible via a search warrant, but they and browser history can give a full picture of your online activity. They can do things like disclose site logins and create more evidence. There is the European law GDPR, and it might change. It does have that thing that pops up that says, like, which cookies do you want to allow? But that can also change how websites react to you. So when you are browsing the web, it's important to be aware that a lot of things are talking to you all at once. This is a huge interconnected network, and that will help you sort of be aware of how to keep yourself safe on the internet. That's it. So if you have any questions, please feel free to reach out and ask them. Thank you for watching.